All right, so in this example, we basically solved a circuit where we computed not only the apparent power here, but we also computed the average power here. And we noticed that there was a discrepancy in the magnitude of the apparent power. Magnitude of the apparent power and the magnitude of the average power. Of course, we noted that they have different units, but they are measuring the same thing. It's the same units, it's just a different name for the same unit to distinguish between apparent power, which is measured in volt amperes, and average power, or real power, which is measured in watts, okay? And so, I didn't write it here, but we could have also written this as 1.349 kilovolt amperes rather than in volt amperes, but it doesn't make a difference. So let's grab some of this stuff that we needed here and let's take it over to the next slide with us. We're going to need the RMS values because we were talking about the discrepancy between the value of the apparent power and the value of the real power, and we want to calculate what that reactive power is. We can calculate that using this formula on the next page for reactive power, Q. Okay, so we have IRMS here, we've got VRMS here. Actually, let's just take all this and make it pretty small and put it up in the top right corner. We'll just put it here, and then we'll go and grab our circuit as well. Again, the reactive power is the amount of power that is basically being produced by the source, but it's not being supplied to the load. It's just oscillating back and forth in the circuit between the electric and magnetic fields that are created when we send energy into a capacitor or to an inductor, which are the reason for our reactive power in the first place. Okay, when we have a purely resistive load, like we did in much earlier in the module, the reactive power goes to zero because the phase shift between the voltage and the current, which is this same phi, that goes to zero. And so if that phase shift goes to zero, the sine of zero is zero, and the entire Q goes to zero, and we have no reactive power, right? We have all real power, which is the case where our apparent power is equal to our real power. Okay? And so one more unit for you guys who are already frustrated by the volt amperes. Q is measured in VAR, or volt amps reactive. Okay, so we've got power, real power, which is measured in watts, W. We've got reactive power, Q now, which is measured in volt amps reactive, or VAR. And then we've got our apparent power, which is measured in volt amperes. Oh, I guess I didn't write that out. I'll just write it as volt amperes. So those are our units. Again, they're all the same. They don't mean anything different. They are still the same unit. They're still energy per unit time, and we're still characterizing power. There are just three different ways to write the same thing so that we can distinguish between so if I just said, if I just saw a value on the side of a machine, this is a machine and it just says 1,000 kilowatts, and we didn't have this standard, we would have no idea whether or not this was talking about real power, or whether it was talking about apparent power, or whether it was talking about reactive power. And so what you will see on the side of machines sometimes is you'll see 1,000 kilovolt amps reactive, and you're like, okay, so you're talking about reactive power. This is the reason for this distinction. Okay, and so we can calculate the apparent power, or we already calculated the apparent power and the real power in our previous example. Let's go ahead and calculate the reactive power. I'm going to grab, I'll just grab these two. I don't think we need anything else. Let's just bring these over. So we already computed these values. We can throw this one right here. We can throw this one right here as well. We'll resize it a little bit. All right, and so let's go ahead and characterize our reactive power for this system. I would say that Q, the reactive power, the amount of power that is not being supplied to the load, but rather is oscillating back and forth in my circuit doing no work, is equal to the RMS of the current, right? Amps RMS, multiplied by the RMS of the voltage, multiplied by the sine of the phase angle between the voltage and the current. Well, I didn't bring those over here with us, but let me grab those too so we have them. Actually, let's just take note. It's negative 20.65, so you guys remember. It'll be 0 minus negative 20.65 degrees, which is going to be Q is equal to basically my apparent power, which we already calculated, which is 1.349 kilovolt amperes times the sine of 20.65 degrees. And that is going to give me, let's see, times the sine of 20.65, and I get 475.7 kilovolt amps reactive, or kilovar. Okay, that is my reactive power. So now we have found the apparent power of our circuit, we found the real power, and we found the reactive power. We have completely characterized the power analysis for this circuit. And so how these three quantities relate, we've kind of touched on it a little bit, but I'm going to talk about it even more in the next video with what's called the power triangle. It shows the geometric relationship between the apparent power, the real power, and the reactive power, and how we can derive, you can basically just look at those expressions and kind of understand where these formulas come from. And we're going to get a good pictorial view of the overall power analysis that we've been doing this entire time. Okay, so I'm going to go ahead and end this video right here. And in the next video, I will show the power triangle, and we'll talk about that a little bit, and then we'll do some example problems.